Hello viewers, welcome to another session on carboxylic acids. We have planned our today's session like this, that first we will briefly review what we had done in our previous session. We will take up the chemical properties of carboxylic acids which we were discussing. Today we will discuss mainly the reactions due to OH group of the carboxylic acid. Then we will take up the reaction due to C double bond O bond that causes reduction mainly, and we will discuss reduction of carboxylic acids. We will take up decarboxylation, then substitution in the side chain and ring substitution in the aromatic ring which is attached to carboxylic group. Finally, we will summarize our today's work. In our previous session, we were discussing about the carboxylic acids and we had discussed their structure, nomenclature, their methods of preparation. Then we started about their properties, and amongst those properties we discussed mainly the physical properties. Amongst the chemical properties we had discussed reactions due to cleavage of OH bond. This is the carboxyl group, functional group, and we had discussed that its properties can be studied at different levels, and the first set of reactions can be where this OH bond is cleaved, and we discussed that oxygen is more electronegative. So, whenever this bond will be cleaved, hydrogen will be lost as H plus ion, and that leads to acidic properties of carboxylic acids, which we have covered in our previous session. Then second set of reactions will be where this cleavage of CO bond is involved and this OH group is substituted. A third set of reaction can be due to this C double bond O bond, where mainly the reduction reaction is to be discussed. Then the reactions where whole of this carboxyl group is involved, mainly decarboxylation is the reaction, and then the substitution reaction on these side chain, which may be an aliphatic or aromatic part, some substitution reactions occur. So, today we will take up all these reactions one by one. Let us start with the reactions which involve this substitution of the OH group. When this OH group is substituted by different other groups, the set of compounds which we obtain, they are called acid derivatives, and there are four common acid derivatives which we study. This is a carboxylic acid. When OH is replaced by a halogen, generally chlorine, we call these compounds as acid chlorides or acyl chlorides, but if it is bromine in place of chlorine, it will be simply called as acid bromide or acyl bromide. Then if this OH is replaced by NH2 group, these compounds are called acid amides. If it is replaced by another alcohol group, basically another alcohol and this acid, they eliminate a water molecule and the products are called esters. And if a water molecule is lost between two molecules of carboxylic acids, the products are called acid anhydrides. So, these are the four type of compounds which are obtained from carboxylic acids where this CO bond is cleaved and this OH group is basically substituted. Let us take these one by one. First, acid chlorides. Acid chlorides can be obtained from carboxylic acids by reaction with thionyl chloride or PCl3 phosphorus trichloride or phosphorus pentachloride. All these will give acid chlorides, and best method out of these three is considered as the treatment with thionyl chloride, because this leads to the formation of both the gaseous side products HCl and sulfur dioxide. So, this reaction can be quantitatively carried out and we will get pure products. Then the same methods can be used even for aromatic acids also, the PCl3, PCl5 or thionyl chloride, and we will get corresponding acid chlorides. When we want to prepare acid bromide, then the reagent used is PBr3 phosphorus tribromide, and corresponding acyl bromide can be obtained. Next, acid amides. Acid amides are obtained from carboxylic acids first on treatment with ammonia, where initially we get ammonium salts, ammonium carboxylate, and these ammonium carboxylates on heating lose a water molecule and amides are obtained. Then esters. Esters are obtained by the reaction of carboxylic acid with alcohol in presence of some acid. Generally sulfuric acid is used for this purpose, because we wish to eliminate a water molecule. OH from here, H from alcohol, and water is lost. The products which are formed, they are called esters. For example, acetic acid, if it is treated with ethanol, we get a compound called ethyl acetate. Similarly, benzoic acid on treatment with methanol gives methyl benzoate. So, in preparation of esters, a water molecule is to be lost if we directly treating it with alcohol. But we have some other methods for the preparation of esters, where we can take some substituted acid like acid chlorides. We will discuss these methods in detail when we will be discussing about the methods of preparation and properties of acid derivatives. Here we are talking about only the properties of carboxylic acids. The next, carboxylic acids, as I said, can be converted into acid anhydrides by a loss of water molecule between two molecules of carboxylic acids. They can also be obtained that if one molecule of carboxylic acid is taken and another molecule of acid chloride is taken. These are mixed and heated in presence of a base like pyridine, where a molecule of HCl is basically lost, which is taken by this base pyridine, and we will get anhydride. Similarly, we can take even the sodium salt of one acid and another acid as acid chloride. Here also a molecule of sodium chloride is lost and we will get anhydrides. Anhydrides of dicarboxylic acids like succinic acid or phthalic acid can be obtained even on simple heating, because here the two carboxyl groups are closely placed and even on heating they lose a water molecule. Succinic acid gives succinic anhydride, phthalic acid gives phthalic anhydride. Then let us take up the reaction due to C double bond O. I discussed in our last session also that this functional group C double bond O is present in aldehydes and ketones also, and due to electronegativity of this oxygen, this carbon acquires a slight positive charge where nucleophiles can attack, and a class of reactions are shown by aldehyde and ketone as nucleophilic addition reactions. But carboxylic acids do not show these reactions, because after the addition of a nucleophile we will have one nucleophile on the carbon and one hydroxyl group, and that gives us a little unstable type of compound. So, generally those additions are not shown by carboxylic acids. Second, in carboxylic acids again there is a resonance between the C double bond O and oxygen of the hydroxyl group, and that reduces the amount of positive charge in carboxylic acids. So, main reaction which is shown by carboxylic acids where CO bond is there, it is a reduction. The addition of hydrogen occurs across this carbon oxygen double bond, and most commonly used reagent for this is lithium aluminum hydride. Actually, lithium aluminum hydride first adds to convert this C double bond O into CHOH, and then one OH which is newly formed, one OH is which is already present on acid, they lose a water molecule and again we get C double bond O, which is further reduced into corresponding primary alcohol. Like this is any carboxylic acid, when it is treated with lithium aluminum hydride, this C double bond O will be ultimately reduced into CH2 and we will get a primary alcohol. You can see in this example, this C double bond O was here and now it is replaced by CH2. We can have some example like propanoic acid, this on reduction will give propanol. Similarly, if we take some aromatic acid like benzoic acid, this CO is also reduced into CH2, so we will get benzyl alcohol. So, the common reaction due to C double bond O of the carboxyl group is reduction. Next, we have reactions where whole of the carboxyl group is involved, and such reactions are categorized as decarboxylation reactions mainly. The reactions whereby carboxylic acid is lost as carbon dioxide, we call that as a decarboxylation. Carboxylic acids undergo this decarboxylation, that is loss of carbon dioxide molecule, and then they give alkanes. This requires heating at high temperature with strong base like sodium hydroxide, and calcium oxide is also added to it to help in the removal of this carbon dioxide. So, generally we call that heating with soda lime. So, main reaction now becomes that decarboxylation of carboxylic acid using soda lime. When a carboxylic acid is mixed with soda lime, initially sodium salt will be formed, and that sodium salt again on heating in presence of sodium hydroxide is giving this alkane, and sodium carbonate is formed, such as sodium ethanoate on heating with sodium hydroxide from soda lime basically will give methane, because one carbon will be lost as carbon dioxide. So, basically what happens, we get alkanes on heating carboxylic acids with soda lime with one carbon less than the total number of carbons present in carboxylic acid. What is the mechanism of this reaction? Mechanism of this reaction has not been fully confirmed, but it is believed to proceed in this way, that the base molecule, that is hydroxide ion chains from sodium hydroxide, will capture H as H plus, then this pair of electron that was forming a bond between O and H shifts between this carbon and oxygen, and this carbon bond with the other part of the molecule, this alkyl group, this dissociates and we get this as anion. So, we get this anion, this is lost as carbon dioxide and hydrogen has gone with base. Now, this anion stabilizes by taking up one H plus from the base, like from sodium hydroxide in that medium, or in the end during the workup of the reaction. If we say that initially on reaction with sodium hydroxide the anion has been formed, again we can show the loss of carbon dioxide in a similar way, that this pair of electron present on oxygen shifts here and this bond is cleaved and this pair of electron goes to alkyl group and we get this anion. Now, next let us discuss the mechanism of decarboxylation, that how actually this loss of carbon dioxide occurs. There has been no fixed mechanism for this which is being confirmed, but generally it is said that the initially formed anion from the acid on treatment with a base like sodium hydroxide, this anion loses the pair of electron in this way, that this pair of electron shifts to form bond between this carbon and oxygen, and then this pair of electron goes to this carbon of the alkyl group and a carbon dioxide molecule is lost from here and we get anion. This anion in the end captures one H plus ion and gets converted into the alkane. But mechanism has been studied in detail in beta carbonyl substituted carboxylic acids. Like dicarboxylic acids, where the one carboxyl group is at a beta position to another, it has been found that this helps in the decarboxylation. Say this is the carboxyl group which is undergoing decarboxylation and this is another carboxyl group present. And what happens? This oxygen captures this H, this pair of electron shifts here, this pair of electron shifts here, and this part is lost as carbon dioxide and we get first the enol form which is then converted into the keto form and we get carboxylic acid. Actually, based on this, the mechanism for the simple carboxylic acids has been given, that here a neighboring carbonyl group at the beta position is capturing this hydrogen and there it is a base coming and capturing this hydrogen and electron from the anion is moving further. Similarly, beta keto acids have also been studied and it has been found that they can also undergo very easy decarboxylation. Here also this carbonyl group present at the beta position of this carboxyl captures this hydrogen and a similar movement of electrons gives this enolic form which tautomerizes into the ketonic structure. So, beta keto acids on decarboxylation gives ketones, whereas beta carboxylic acids means dicarboxylic acid having another carboxyl group at beta position gives simple carboxylic acids. And this is the basis of malonic ester synthesis which we will study later. Then another reaction where this decarboxylation occurs but in a slightly different way, that is studied under Kolbe's electrolysis. When sodium or potassium salts of carboxylic acids are electrolyzed in their aqueous solution, that is in presence of water, we get alkanes. But the alkanes which are formed are those which are having double the number of carbon atoms then present in the starting carboxylic acid -2, because 2 carbons are lost as 2 molecules of carbon dioxide from here. So, the alkyl group that is left after the loss of carbon dioxide joins with the alkyl group for another acid and we get corresponding alkane. For example, if a methyl group is here, if we have sodium methanoate, the product formed will be ethane. Now, let us see how this reaction proceeds, that is what is the mechanism for this Kolbe's electrolysis. In this case, what happens? We have the aqueous solution of the sodium salt of carboxylic acid. So, we get anions and cations, that is sodium ions, and the anionic part is a carboxylate ion. When electricity is passed through, that is electrolysis is started, these anions will move towards anode and cations will move towards cathode. Now, let us see what reaction occurs at anode. At anode, this anion loses electron, because you know that anode always oxidation occurs which involves the loss of electrons. So, one electron from this carboxylate anion part is lost and we get this radical. Then in this radical, cleavage of this alkyl C bond occurs and this portion is lost as carbon dioxide and we get this alkyl radical. This cleavage is a homolytic cleavage here. So, one electron goes with the carbon, one electron remains with this alkyl and carbon dioxide is formed and alkyl radical is formed. Then two such alkyl radicals combine to give alkane. So, this is the stepwise progress for Kolbe's electrolysis. Then what happens at cathode? The sodium ions, they move towards cathode. There they take up the electron, means a reduction occurs, they form sodium metal. The sodium metal immediately reacts with water, forming sodium hydroxide and hydrogen gas. So, at cathode hydrogen is liberated and at anode we get the corresponding alkane. Dicarboxylic acids also undergo this Kolbe's electrolysis, but they give slightly different type of product. Let us take the example of potassium succinate. When potassium succinate is dissolved in water, initially these succinate ions will be formed and potassium ions. At anode, these succinate ions will lose the electrons. So, there are 2 carboxylate anions, 2 electrons are lost and we will get corresponding radicals. The reaction proceeds in the same way as it was in monocarboxylic acids. In the next step, this carbon-carbon bond undergoes homolytic cleavage, carbon dioxide molecules are lost and we get the radicals here. So, now what happens? After the loss of 2 molecules of carbon dioxide, we get this diradical. Now, as we studied in this simple carboxylic acids, that one radical combines with another radical. So, there is a possibility that one of these diradical may combine with another similar diradical to give cyclobutane. But a much faster and easier step is that these 2 carbons may form a bond to give ethene, and actually ethene becomes the major product in Kolbe's electrolysis of potassium succinate. The next is the thermal decomposition of calcium salts. It is also a sort of decarboxylation. Calcium salts of carboxylic acids, on heating, they lose a molecule of calcium carbonate and products formed are ketones, RCOO. There are 2 carboxylate ions because calcium has a valency of 2. One oxygen is left and remaining is lost as calcium carbonate. So, ketones are obtained as a product. Say if I take with calcium formate, means R is hydrogen, then what will happen? We will get methanol, formaldehyde as a product, HCHO. If I take mixture of calcium formate and calcium salts of some other acid, right, this is calcium formate, this is calcium salts of some other acid. Now, there is a possibility that one portion from this acid and one portion of this acid may combine to give a product. In such case, now what happens? This molecule gives ketone, this molecule gives methanol, and the product formed by the cross of these two will be this aldehyde. Then silver salts of the carboxylic acids, they also undergo a reaction on treatment with bromine especially, and that is a name reaction called as Hunts-Decker reaction. A carboxylic acid reacts with silver oxide to form silver carboxylate, that is silver salt of the carboxylic acid. The silver salt on treatment with bromine undergo the loss of carbon dioxide and alkyl bromide is formed. So, this is one specific method for the preparation of alkyl bromide also. Then the reaction in the side chain. As I said that one set of reaction can be on the alkyl group or aryl group which is attached to carboxylic acid. In case of aliphatic carboxylic acid, obviously the side chain is alkyl group, and when halogenation of such acids is carried out, a halogen group is introduced at the alpha position. We call it as a alpha halogenation of aliphatic acids, and again this is the name reaction. It is called as Hell-Vollard-Zielinski reaction. In this reaction what happens? Say this is a carboxylic acid and it is treated with halogen. Reaction is carried out in presence of phosphorus or phosphorus halide. One of the hydrogen at this alpha carbon, it gets substituted by the halogen and we get alpha halocarboxylic acid. These reactions are generally successful when halogen is chlorine or bromine. Good yields are obtained. Let us take an example of this reaction. Say this is propanoic acid. When it is treated with one equivalent of bromine, I am specifically saying one equivalent of bromine, then we will get this alpha bromo propionic acid or 2-bromo propanoic acid. But if this bromine is in excess and our starting compound also has got more than one replaceable hydrogen at the alpha position, then polyhalogenation may also occur. Say if it is like RCH2COH, there are two replaceable hydrogen here and we take halogen in excess, then in two steps both the hydrogens can be substituted by halogen. First we will get monohalogenated derivative and then in second step second hydrogen can also be substituted and we will get a dihalo compound, but the two halogens will be at the alpha position. These alpha halogenated acids are very useful for the preparation of alpha hydroxy acids, alpha amino acids, or having unsaturated group, that is by the loss of HBr or HX from these two positions. We will discuss about these unsaturated and substituted acids in our next session. Then if this carboxyl group is attached to some aromatic ring, that is we are talking about aromatic carboxylic acid, then substitution will occur on the ring and carboxyl group acts as a deactivating group and a meta directing group for electrophilic substitution reaction such as nitration. You are familiar with these electrophilic substitution reactions. These are basically 5 reactions: nitration, sulfonation, halogenation, Friedel-Crafts alkylation and Friedel-Crafts acylation. Let us talk about nitration. This benzoic acid undergoes this nitration in presence of concentrated nitric acid and concentrated sulfuric acid, requires heating and we get meta nitrobenzoic acid. The nitro group is introduced at the meta position and the conditions required for this reaction are more drastic than simple benzene because this carboxyl group is acting as a deactivating group. Similarly, in case of sulfonation, benzoic acid is treated with oleum. Oleum is sulfuric acid having excess of sulfur trioxide and we get again a substitution occurring at the meta position, but here for the nomenclature main functional group is considered as sulfonic acid. So, this compound is named as meta carboxybenzene sulfonic acid. As far as halogenation is concerned, carboxylic acid react with halogens in presence of ferric halide, we get corresponding meta halobenzoic acid. Again here the reaction is good for chloro or bromo derivative preparation, that is when halogen is chlorine or bromine we get better yields. As far as Friedel-Crafts alkylation and acylation reaction are concerned, carboxylic acids do not undergo these reactions, or if at all under certain conditions we get the corresponding product, yields are very poor. So, this was about the carboxylic acids which have aromatic ring attached to them which undergo electrophilic aromatic substitution reactions. So, let us summarize what we have discussed today. We started with the chemical properties of carboxylic acids and we discussed that properties can be studied under different headings depending upon the type of bond involved at the time of reaction. We discussed that when OH group is substituted where CO bond is cleaved, we get derivatives of carboxylic acids known as acid halides or acid chlorides, amides, esters and acid anhydrides. Then carboxyl groups can be reduced using lithium aluminum hydride into corresponding primary alcohols. Decarboxylation of carboxylic acids can be carried out under different conditions. Heating with soda lime gives alkanes. Kolbe's electrolysis also gives alkanes, but these two give different type of alkanes. Then with silver salts and bromine we get alkyl bromides. Calcium salts on heating gives ketones or aldehydes. We discussed the substitution in the side chain. In the alkyl group of aliphatic carboxylic acids, the reaction involved is Hell-Vollard-Zielinski reaction, where alpha halogenation occurs, and aromatic carboxylic acids undergo ring substitution. That is all about the chemical properties of simple carboxylic acids. In our next session, we will discuss about some substituted carboxylic acids like hydroxy acids and haloacids. Thank you.